All right, future architects, welcome. Today, we are going to tackle a structural concept that, I know, sounds a little intimidating, but trust me, torsion is actually a secret weapon for the AREs. We're going to break it down so simply, you'll be wondering why you ever thought it was complicated. Okay, let's just dive right in.
So, let me start with a question. You've seen the footage of an earthquake, right? And you wonder, why do some buildings seem to just twist themselves apart? It's not random. There is a super powerful force at play. And by the end of this, you're going to understand exactly what it is and, more importantly, how to design against it.
So here's our game plan. First, we'll uncover that hidden twist. Then, we'll look at the structural balancing act that causes it all. After that, we'll dig into the code's very clever safety net. Then we'll build your ARE playbook. And finally, we'll get into the nitty-gritty of how this stuff shows up differently on the PPD and PDD exams.
Okay, let's get right to it. What in the world is this hidden twist?
You know, when it comes right down to it, torsion is just a fancy word for twisting. That's it. When a lateral force, think big wind gusts or an earthquake shake, doesn't hit a building's strong point dead on, the building is literally forced to rotate. And that rotation, that is torsion.
To really get this, you gotta know the two key players in this drama. First up, you have the center of mass. Just think of this as the building's center of gravity. It's where a big lateral force effectively lands its punch. And on the other team, you've got this center of rigidity. This is the structural core, the tough spot around which the building wants to resist any push. The entire game really is about how these 2 points line up. And that leads us straight to this balancing act. The alignment, or, the misalignment of these two centers, it dictates everything that happens next. So this all plays out in two very, very different ways. In a perfectly symmetrical building, the center of mass and the center of rigidity line up. A force comes along, pushes it, and the whole building just kind of slides. It's predictable, it's stable, that's a happy building. But in an asymmetric building, those two centers are offset. So now, when that same force pushes the center of mass, the building is forced to rotate around its stronger center of rigidity. It twists, and that is a stressed out building. That stress is exactly what causes all the damage.
So here's the chain reaction, broken down into 3 simple steps. 1. The lateral force hits the center of mass. 2. That distance between the two centers, we call that eccentricity. It acts just like a lever arm, and it creates a rotational force, which we call a moment. And 3. That moment forces the building to twist, which creates a ton of torsional stress. It's a domino effect. You have to stop before it starts.
But let's be real. In the real world, no building is perfectly symmetrical. So how does the building code deal with this? Well, it uses this really clever safety net. The International Building Code is pretty smart about this. It knows that even if a design looks perfect on paper, there are always going to be tiny imperfections in the real world, in the materials, in the construction. So it makes us plan for something called accidental torsion. Basically, we have to design as if the centers are already a little bit misaligned from the get-go. And here it is. This is the magic number you absolutely need to remember for the exam, 5%. The code says we have to do our calculations assuming the center of mass has shifted by 5% of the building's dimension. This makes sure there's a built-in margin of safety for any weirdness we didn't plan for. So if your building is, say, 100 feet wide, you have to design as if that force is hitting 5 feet off center, period. Okay, enough theory. Let's get practical. This next part is your playbook for any torsion question the ARE decides to throw at you. First things first, let's nail down the causes. Number 1 culprit, hands down, is that misalignment we keep talking about, eccentricity. This usually happens when you put your heavy-duty structural stuff, like shear walls or braced frames, on one side of the building, but not the other. And like we're about to see, certain building shapes are just asking for trouble. So how do we fight back? Well, the solutions are basically the mirror image of the problems. You want to aim for symmetry in your structural plan. Balance your shear walls. A fantastic tool is a rigid diaphragm. Think of it like a super stiff floor or roof that acts like the lid on a shoebox. It forces all the walls to move together and spreads the load out nice and evenly. And, of course, if you can, avoid those tricky shapes. Now, let's call out the usual suspects when it comes to shape. L shapes, T shapes, U shapes, they're all inherently a problem. Why? Because they create what we call re-entrant corners. You know those inside corners where the shape folds back in on itself?
Well, during an earthquake, those corners become stress magnets. They just attract and concentrate all the torsional forces, and that can lead to failure. The ARE loves to ask about these shapes.
All right, here's a pro tip for test day. Torsion is going to show up on both the PPD and PDD exams, but they test it in really different ways. And understanding this difference, that's key.
Okay, listen up, because this is how you're going to unlock these questions. On the PPD exam, the focus is all conceptual. They're going to ask you about the why. Questions like, hey, how can you reduce torsion in this plan? The keywords to look for are symmetry, rigidity, eccentricity. Then you get to PDD and things get technical. Now they're asking about the how, like where exactly do you put the shear wall to resist this specific load? The keywords there are all about specific systems, shear wall placement, diaphragm action. Seriously, just knowing this distinction is half the battle. So look, if you walk away remembering just one thing, let it be this super simple formula. Torsion equals a lateral load plus eccentricity. If you can get rid of that eccentricity by lining up the center of mass with the center of rigidity, you've pretty much conquered torsion. It really is that fundamental. And that's our deep dive on torsion. So here's a little challenge for you. Next time you're walking around, start looking at buildings differently. Can you spot the L shapes, the U shapes? Can you kind of guess where the structural core might be and what the potential torsional risks are? Keep thinking, keep looking, and you are going to be ready to absolutely nail this on the exam.